Good morning, everybody. As promised, this is a review of Quiz 12 that we took on Thursday. I am a couple of days late getting this done. I have not been feeling all that great, and one of my kids decided to share their germs, which is always super fun. So, if you'll remember this section, we're dealing with strong acids and strong bases and titrations of those acids and bases. So, we've got one question with 4 parts. 20 mils of 0.08 molar hydrochloric acid, which is a strong acid, titrated with an unknown volume of 0.0500 molar potassium hydroxide, which is a strong base. What is the pH prior to the addition of any of the potassium hydroxide? So this is a pretty easy calculation because if you'll remember, when hydrochloric acid you put into water, that's going to dissociate into H plus and Cl minus. Cl minus is not going to have anything to do with anything when it comes to pH. So we already know our concentration of hydrochloric acid, which is going to be the same as our concentration of our hydronium ions. So we're going to plug that into the pH formula. pH is the negative log of 0.08000, and that is going to give us the pH. All right, so when we run those numbers, we get a pH of 1.0969. Remember your significant figures, which are actually quite a few significant figures, so you would be okay leaving it this way. I would probably shorten it. I would shorten it to 197, just round that last digit up. Now, the equivalence point volume for the titration, that is where you're going to do, make sure you guys can see you got your molarity of your acid times the volume of your acid. We're going to set that equal to the molarity of the base times the volume of the base. Now, if you've got like a diprotic, then you can put your number of moles of your acid and the number of moles of your base on the bottom of your fraction, and that will account for differences in the number of moles needed for the reaction. For our reaction, it's a 1-to-1 ratio, so we don't really need to worry about the N, but it is a good practice to put it in there just in case you're dealing with something like that has more than one hydrogen that it's giving up, like a diprotic acid or a diprotic base or something. So it's a good idea to put it there just for practice, get in the habit of doing it, and then you'll do it regardless, and you will get the correct answer on your questions. So we're looking for the volume of the titration. Now let's see what we've got to start with here. We got 20 mils of HCA, so that's this one. We've got our molarity of our HCl, we got that. And then we've got our molarity of the base. So we're looking for the volume of the base. And sometimes it's easier to just go ahead and rearrange your equation before you put any numbers in. So the molarity of our acid times the volume of our acid. We don't have to worry about N, so we're just going to mark those out. And as these two are being multiplied, we're going to divide away to get VB by itself. Divided by the molarity of the base is going to give you the volume of your base. And then let's plug in some numbers. I am going to leave this in milliliters. You can put it in however you want. It does not really matter. But I'm just going to leave it in milliliters for now. Running out of room. And we're going to run that through the calculator and see what we get. Alright, and that gives us a volume of 32 milliliters, which if we wanted to put that into liters, that would be 0.032 liter. Now, the next question, this is going to be the easiest on this whole quiz. What is the pH at the equivalence point of the titration? for strong acids and strong bases only, your pH at the equivalence point is always 7. Okay, pH higher than 7 is going to be basic. pH lower than 7 is going to be acidic. But with potassium hydroxide, it goes to potassium and hydroxide. And then hydrochloric acid, it goes to hydronium and chloride ion. Potassium and chloride have no effect on pH at all. That's just a salt. It is what it is. But you have, because they're at equivalence, you have the exact same number of moles of hydroxide and as you do hydronium. And so they just create water. And water, pure water with nothing else in it, is a pH of 7. So that is why that is that way. So this one, we're going to have to do a little bit more math because we're dealing with a system that is not at equilibrium, okay? So it says, what is the pH following the addition of 25 mils of potassium hydroxide? So we've already discovered that 32 mils gets us to our equilibrium point, so this is going to be before our equilibrium point, and we're going to have to figure out how much of our hydrochloric acid we're going to have left over. And in order to do that, we've got to convert everything from molarity, which is moles per liter, to just moles. All right, so we're going to start with our hydrochloric acid. So we've got 0.020 liter. Multiply that by this is, if you write it out this way, this is a good way to realize that your units do cancel and it leaves you with moles. So it might just help you keep it track in your head a little bit with how you do that. And then we're going to get an answer to that, but I'm going to go ahead and write down the second equation. So all right, and I just realized that this should have been 25 here, not 32. So I'm going to see if I can get a different color and make that stand out a bit more. .025 liters. There we go. So this one here is going to equal up to 1/6. This is going to give us 0.00125. And we're going to take our larger number and we're going to subtract our smaller number to it to get how much is remaining. All right. So how I like to do this, I'm going to turn this so you guys can see a little bit better. First of all, let's label these, okay? So this is our base, and this is hydrochloric acid. That'll help in a minute. Remaining, we're going to take and that's going to give us 3.5 times 10 to the negative 4 in scientific notation. Okay, so this is going to be, we've got hydrochloric acid is what is left. But that's also going to be the same when we're looking for pH. Remember, your chlorine doesn't do anything as far as affecting your pH, so that's the hydrogen ion concentration. So we're going to plug this number into our pH solution. And that's going to give us a pH of 3.456 as our answer for this one. Again, if you guys have any questions, oh, you know what? That's not correct. because we did not divide this by our total volume. Well, hell, let me fix that. Okay, little word for advice for anyone who wants to make chemistry and math videos online and you're sick. Make sure that you're thinking clearly when you start. Okay, so our total volume, we've got 0.020 plus 0.025. Okay, and we're going to divide our 3.4 times 10 to the negative 4 by that total, which is 0.045. And that is going to give us 0.00755. And this is going to be our hydrogen ion concentration. So the 3.5 times 10 to the negative 4, that was moles, okay, which is a type of concentration measurement, but we have it in solution, so we have to measure it in solution in order to get the pH. So this is the number we're going to plug into our pH calculation. And that is going to give us 2.12 for our pH. Okay, so not a huge terrible difference, but it is enough of a difference that you would be marked incorrect if you didn't divide by your volume measurement there. If you guys have any questions about this, let me know. I will be making some videos to go over the materials for the next quiz, which will be quiz 13. Hopefully my voice will hold out that long, and I will talk to you guys later.